Good afternoon, or should say immediately pre-noon for those of us on the West Coast. But it's afternoon for our guest today. We have Rachel L. Smith, PhD, who is coming in from the Astronomy and Astrophysics Research Lab at the North Carolina Museum of Natural History, where she's also the curator of meteorites and the associate professor of Appalachian State University Physics Department, Physics and Astronomy. She's joining us here for our cosmic conversations, which I will be emceeing and kind of providing a little bit of color commentary. My name is Josh. I'm from Morrison Planetarium, and we are delighted to be broadcasting this program out to you on our weekly Cosmic Conversation spot. Now, this is actually one of the programs we are sending out to our friends over at OpenSpace YouTube channel as well. If you are a fan of OpenSpace, this is going to be a really cool use of that software. And if you're not a fan yet, make sure you download it and check it out. You can find it at the openspaceproject.com. Now, you can actually see our OpenSpace software. Our producer, Mary, is showing it to us. This is a pretty cool archery target you're showing us, Rachel. Can you tell us a little bit about what this is and what we use OpenSpace for?
Yeah. Thanks, Josh, for the intro. And it's really exciting to do a program for you guys. This is a really fun project, and we're partners with you and the American Museum of Natural History. And I'm excited to show. So these are just a few, there are maybe a few thousand of these asteroids that are orbiting the sun, and they are between Mars and Jupiter. So what I'm showing you are only a handful, really, of the asteroids that are in our solar system. This is part of the small bodies database that has been imported into OpenSpace. And we see the inner asteroid belt, which is the yellow ring here, and the outer asteroid belt here, and there's a whole main asteroid belt. The reason I didn't turn it on is sometimes with OpenSpace, when you put a whole lot of data in at once, it doesn't stream as well, but users at home can add it in and see all those really cool asteroids. And then the red ones are called potentially hazardous asteroids, and they're the ones that could potentially hit Earth. And we only know of about 25,000 near-Earth asteroids like these, and that's still a small sample because we can only detect up to only about 150 kilometer diameter or larger. And the reason I'm showing these is because we're going to talk a little bit about astrobiology today. And when we think of astrobiology and search for life, we also have to think of what's in our solar system that could affect life on planets, and certainly asteroids are some of those objects. And I think they're pretty cool.
That sounds awesome. So along the way, if folks have any questions, throw those in the comments. We'll do our best to respond to questions as they pop up. But to get us started, I'm noticing at like 60 degree, maybe 120 degree intervals, like thirds around the outer asteroid belt there. There's weird bumps. Kind of looks like Mickey Mouse ears when you have the bottom one cut off. What's going on there?
I'm sorry, where exactly are you looking?
So along the plane, separated by about 120 degrees, sort of at equidistant thirds, there's bumps.
I see, here and here.
What's making that happen?
Well, you have some resonance with, so this is the orbit of Jupiter, this planet here, and you have some resonance with Jupiter. And so if I turned on, in fact, I wasn't going to do this, but I could do the Trojan, let's see where they are, or Jupiter family. No, not that, sorry. Little, there we go. If you look, it's similar. If you look at the Trojan asteroids, these really show, and I'll zoom out a little bit, these really show how Jupiter affects our solar system. So Jupiter is by far the most massive, and I'll actually turn off the automatic rotation. Jupiter by far is the most massive planet in our solar system. In fact, it almost is the size of a brown dwarf. And if it had grown a little bit bigger, it could have been a star in our solar system, which could have effects that we don't, who knows, maybe we wouldn't even be here. But what Jupiter does is it affects mass in our solar system. So these are called resonance points. And these Jupiter family comets and all these little mouse ears that you were talking about are due to the effects of gravity on Jupiter and holding these particular asteroids in a rotation with Jupiter because of the gravitational pull of Jupiter, essentially. And we see these resonant, and then you have big gaps in the asteroid belt as well. And these gaps are also caused by Jupiter. And we can really thank Jupiter for a lot of the of not being hit by nearly as many asteroids and comets as we could have been in the past.
That's pretty awesome. I don't want to distract you too much. It sounds like you had a full program, but that was a really cool thing to point out.
No, I really loved talking about asteroids, and I'm excited because OpenSpace now has the latest version, has the asteroids and comets, and that's super exciting for me. So these are the asteroids, and thinking about how often will we be hit by asteroids and comets, and really, actually, I'm going to leave these on. I'm going to zoom in. We're going to go to Earth now, and we're going to make a few stops on Earth. And the first stop is Meteor Crater. So we have been hit by asteroids in the past, and we will be hit again. How big those asteroids are is, we don't really know when the next hit will be that will affect life on this planet. But the bigger the asteroid, the less likely it will hit our planet. And we are hit by asteroids, little pieces of rocks from space every single day. And the cool thing about asteroids, and this gets at, I'm actually going to, at this point, turn our trails off. And you'll see the menu pop up here. This is something that you can do at home. You can play with OpenSpace. You can turn data sets on and off. And that's what I really love about this software, is you can manipulate data sets and really explore how turning them on and off changes views and vantage points of really the entire universe. And we're only going to make a few stops today. Oops, I turned on the wrong thing. Sorry about that.
I noticed we were taking our trip to Mauna Kea, but it's nice to take a tropical vacation.
This is subconscious because I actually really want to go to Mauna Kea. I'm supposed to be observing this year. I observe on the summit of Mauna Kea. And what's disappointing, of course, is with COVID, I haven't been able to go. So I instinctively just went there because I really just want to go. I'd go right now. But no, it's not safe to travel.
We had a question come in from Christine. If someone were interested in meteorites and asteroids, are there internships or ways to pursue that?
Yeah, that's a great question. There certainly are internships that pop up. And I don't know personally right now of openings, but essentially getting to know people at museums. You can encourage Christine you can send me an email. If you go to the Museum of Natural Sciences website, there's emails. My colleagues at the American Museum of Natural History there's a whole department there. So if you contact people at museums that have collections, they can help at least discuss, the career options. But yeah, they come up periodically for sure. These spheres, by the way, are markers. They're like little flags that we have on to find stuff easily with OpenSpace. Sometimes we don't. Sometimes we lose. Let's see here. What am I doing? As I'm talking too much. There we go. So let's go back to Meteor Crater. So Meteor Crater is one of my favorite spots. You can visit Meteor Crater. It's near the Grand Canyon, which you may have seen as we passed over. And the Grand Canyon is really pretty spectacular. It's an amazing feature on our planet, but when we look at comparative planetology, it's really dwarfed by the canyon on Mars. And we're going to go to Mars today and talk a little bit about that. So when we think of Meteor Crater, I really like this crater. This is data sets coming in, by the way, the gray.
Not big gray rectangles all over Arizona.
Remember that with OpenSpace, it's all real data. And so OpenSpace is pulling in data as we speak for Earth. I left the asteroids on so you could see, if you looked up in the sky, of course, you wouldn't see all the asteroids streaming in. This would be an amazing meteor shower, by the way, if this were actually real.
Terrifying, I think.
A little terrifying, maybe. But this is just what's cool about OpenSpace, and I'll just zoom out a little bit to show you guys, is we have all the actual locations of these objects. So when you see asteroids and comets and star fields, when we get out to space, and the locations of moons and everything, that's all accurate. And you can manipulate time. You can manipulate where you are in space, like turning your camera, essentially like a spaceship or a camera, to visualize different parts of planets. And so when we think about the data we have as scientists to visualize the universe, where there are places we've been, of course, Earth is the first place we've been, right? And then there's Mars, where we've landed robots on Mars. And then there are places we haven't been, but we know where they are. And so we have two-dimensional space to work with as well. And so everything's accurate in OpenSpace to the amount of knowledge that we have, and the data are pulled in for us to visualize all of these really cool places. And you can fly all around the universe with real data sets, which is super awesome and unique about this software. So Meteor Crater is pretty awesome. It's a highway. The famous joke is, isn't it great? It fell near a highway. But that's not accurate, of course, because around when this was 50,000 years ago, you had these cuties, the woolly mammoths, and you had giant sloths. So this was the Pleistocene, when it was much cooler and wetter in this region than it is now. And so you had all of these really cool animals. Now, what would they have seen? Well, they wouldn't have gone, this is not an extinction event by any means. It's a fairly small crater. It looks amazing when you're there, but it's really not a big hit. But they would have maybe witnessed a fireball coming in and some damage, to their, I guess, tree homes or wherever they lived.
Wouldn't have been fun to be underneath it when it fell, for
Probably
sure.
not. Probably not. Yeah, exactly. So I'm just going to, so when we think about astrobiology, just think about thinking about the search for life beyond our planet. We think about meteors and delivery of material. Not only does impacted planets, of course, affect like extinctions and the dinosaur extinction, and we think about that when we think about asteroid hits, and the recent one in Russia a few years ago, which hit the city of Chelyabinsk, but also the delivery of materials. And we don't know how Earth got its oceans. We are 75% covered in ocean, and how we got the materials we need for life. And so when we think about the stuff in space that we all came from, the asteroids and comets, these are the remnants of our beginnings for roughly 4.5 billion years ago. We also need to think about, these are the delivery mechanisms from space. And we have a lot of evidence from meteorites and from comets and asteroids that there's a lot of water out there and organics as well.
Now, Rachel, to give folks a sense of perspective, Carter asked, how big was the impactor that caused Meteor Crater?
Oh, yeah, thanks. Is this my friend Carter? Maybe.
I believe so. He might know the answer. Just testing.
It's about 3 times the diameter of this crater. So it's, 3 times smaller. So you get an explosion over the atmosphere. So I think this is about a mile across. I could be wrong about that. But the crater is about 3 times roughly or so, order of magnitude, the diameter of the actual impactor of the explosion. So what happens is it explodes before it hits the ground. You don't ever have a big giant asteroid sitting in the ground. It explodes due to the pressure differential in how it's impacting, if it doesn't all burn up like a little particle. So this one would have exploded. It creates a much bigger crater than the actual impactor. So it's many, many times. Nature delivers much more equivalent of TNT than we could ever manufacture in a bomb. And that's a really scary comparison, but it's true. Even the bombs that we used in the war, in World War II, are nothing in comparison to the explosive events that we get from space. I hope that answers your question. I don't remember exactly the diameter, but it would be roughly 3 or 4 times smaller.
Steven's got a really cool question. I think we might address this a little later. Do you think RNA microbiology is a possibility on the outer planets and moons of our solar system?
Yeah, that's really interesting. There's a theory, the RNA hypothesis, that's possible. It's possible that first of all, RNA is simpler than DNA. It's single-stranded, and so there's a lot of thought that a life started. The first life could have been RNA, like an RNA virus. And a virus is sort of this weird, maybe life, maybe not life. It needs a host to reproduce, but we can have RNA viruses. And RNA, being simpler, could likely evolve first. And so the idea of primitive life, extreme life, and this is what we're about to talk about next, where we go to our, hello, San Francisco, I'm talking to you. I visited you very fast. Here you are. From North Carolina, is the fact that, when we talk about extreme life and the life that we think could survive in the harsh environments of space, RNA microbes could be, my microbes I use loosely, bacteria-like, virus-like, maybe could be in harsh environments, not only in the outer reaches of the solar system, but also maybe Mars or Europa. I mean, this would be primitive life. We're not talking about it. For a lot of reasons, RNA life is not, we don't think of it as being complex life for lots of reasons in how RNA replicates and genetic diversity. But certainly it's possible. And that's been a hypothesis, very interesting hypothesis out there. So where we are now, as I was blabbing away, these are the San Francisco salt flats. And some of you may know this region. This is right where, and I left the asteroids on again. This is near the San Francisco airport. These are very colorful ponds. They're manufactured ponds, and they're meant for salt mining. And actually, I can zoom down. I'm going to go back to Earth, see if I can hopefully not miss it. When I zoom, I can drive better. when I center on Earth. There we go. So these salt flats are really cool. This is one of the regions of analog environments that we can actually see with OpenSpace. We can't go under the oceans yet. Something for Michael, if you're listening, get us ocean. No, I mean, software developers, get us under the ocean. But there are a lot of extreme environments. And by extreme, we're comparing that to life as we understand it. And this is the salt flats of San Francisco. These ponds are one of the regions on the surface of Earth that is extreme, meaning it's got a really harsh environment for most life to survive. And yet there are microbes that live inside salt. And so this is where the colors come from, or from the enzymes in these microbes. And so astrobiologists are studying these ponds to see if they can understand these analog environments and possible analog life to what we might find in the briny ocean, the salty oceans of Europa, or maybe even under the surface of Mars. There's a little bit of water that might be percolating up even on Mars now. And so this is the type of life that's still DNA. It's not RNA-based life, but still it's very harsh and it's a harsh environment, similar possibly to what we might find in space. So we think about, what kind of life are we looking for? Well, the first kind of life we're looking for are the microbial organisms that might be in our solar system. And then the very last bit of this program, we'll talk for a few minutes about SETI, which is the search for extraterrestrial intelligence, which is what everybody wants to talk about, right? I really think these are beautiful, and they are analogs to Mars in several respects. So, and you can see them outside the plane if you fly into SFO. So we're going to go, nice thing about OpenSpace too, I'm going to turn off the asteroids real quick because they do slow things down a little bit.
While you're clicking off stuff, a quick response. We had a question from Phelan show up. If folks want to see sample videos of asteroids hitting planet Earth, I've got to give a plug for our show, Asteroids Incoming. So if you want to check that out, we've got cool stuff on the Academy website. You can see some video clips. But if folks wanted to see scientifically accurate asteroid hitting videos, where do they go? Because we know Hollywood struggles with this.
I mean, it's unfortunate, but the best videos, the only real videos we have now were taken, well, there are some you can find online if you do like a Google search, but the videos that we think about now there was a lot of footage for the Chelyabinsk hit in 2013. And the reason is that there were a lot of dash cams on the on cars that filmed the fireball. And there was security camera footage of the fireball coming in. And it's not, of course, polished like you'd expect from a film, but it is accurate and it's genuine. It's genuine, right? Exactly. Yes, exactly. Genuine, and also, it's pretty terrifying because the people experiencing this thought they were under attack, and they were. Just was from space, and not from our friendly neighbors in space. But I actually have some security cam footage that someone gave me, which I show in program of the impact. And I can't import videos into OpenSpace yet. It's another thing, developers.
Poor Micah, we're going to give him a big laundry list by the end of the program.
Micah is our friendly software developer who's also gets to hear our complaints. But actually,
it looks like we're heading to Turkey.
Yeah, we're in Turkey now. I was driving as I was talking, which is better than driving and texting, but still.
Much safer in open space.
Much safer in open space. Yes, we're in Turkey, and the reason we're here, we were talking about analogs to Mars, and the reason we're here is this lake is called Lake Salda, and this is a really interesting place that I actually just learned about. I think it's gotten a lot of press lately because of Mars 2020, which is the rover that's headed to Jezero Crater on Mars, and is due to land next year in February. And we're going to go there as well. It's a very unique lake. It has these microbiolites. So essentially this white rim around it's a recreation area now for people, but this white rim around the shoreline here is made by deposits from microbes. And it's actually a pretty unusual place. It's the scientists studied this lake to explore what they might find on Jezero. And there are microbial mats that exist around this lake. And they are going to sample, Mars 2020 will sample the shoreline of Jezero Crater to see if there's evidence for fossil microbes, or even maybe not fossils, maybe extant or living microbes. It's a pretty spectacular lake. You can explore all around Turkey. You can barely fly anywhere now, but you can go with OpenSpace, so that's nice. As you saw, I took you all to Mauna Kea. If it was up to me, we'd just be sitting on the beach in Hawaii for the whole program. No, I'm joking. So yeah, it's a really cool place. And keep in mind, this is where water, there's a delta here where water flowed in. And this is actually very similar to the geography that we see on Mars. And we'll come back to this, thinking about Lake Salda when we get to Mars. But the last stop, and this goes into a little bit of my research that I do. I'm an observer, and I use the telescopes on Mauna Kea to look at forming stars. And we think about forming stars. Why are forming stars important? Well, they're analogs to when our solar system was forming 4.567 billion years ago. And to think about that, we have exoplanets. And where am I here? My exoplanets. I'm going to turn them on. So I'll leave them on for the rest of the program. And again, what you see here are locations of the exoplanets. We have not been to the exoplanets, but we know where they are. And now we go to Mauna Kea. And we know where the exoplanets are, and we have an inventory of these planets. Many are Earth-like. We know where they're locally near in what we call our local neighborhood of several thousand planets. And it's quite possible that every star has a planet, at least one planet. And that would mean there are billions of planets in our galaxy that could be like Earth. But all we know from a scientific standpoint is if the planet has a rocky surface or a gas or ice giant, and if it's close enough to its star to have liquid water on the surface. And so you see here, I'm going to turn off the little, because I know where we're going now.
Important things to know.
Yeah, I mean, when we think about searching for life, we think about water and carbon, and Earth is 75% covered in water. You can see my cursor, right?
Yeah.
Yeah, okay. And so we look for liquid water on the surface, and then sometimes we consider liquid water under the surface, like on Europa, the moon of Jupiter, which will hopefully fly by if there's time. And so we're thinking about life that needs, all life as we know it needs water, and all life as we know it is carbon-based. And so for the work I do, I'm looking at early chemistry of forming stars. So way before planets form, but still we're considering the chemistry that's important for planets to form, and also for the molecules that we need for life. So I'll just zoom out a second. So this is the big island of Hawaii. This is Mauna Loa. This is Mauna Kea. And then Kilauea, which is the active volcano, is actually below, down in this region of Hawaii. And so it's not in a region of active volcanism. There's a small percent chance it could be active again here on Mauna Kea. But what's cool about Mauna Kea, not just because it's a beautiful place for astronomy, it's a shield volcano. It's exactly how the volcano on Mars, Olympus Mons, formed. And we can we can understand, we understand a lot about our own planet by studying other planets as well. And we're learning a lot of this comparative planetology by going to other planets, and it's really important to keep exploring space. And with OpenSpace, you can do this with the great data that we have with OpenSpace.
It's a big mountain.
It's a big mountain. It's a big mountain area. And so these little anthills, which they look like little anthills, are actually cinder cones, and they're part of the byproduct of the volcanism. This is the saddle road that you drive up to get to the summit. There are all these telescopes on the summit here, and there's a place that you stay at about 9,000 feet. It's a 14,000 foot summit. And the telescope I'm using now, I'll zoom down. Hopefully you're not getting too motion sick. I also drive my car like a maniac, just in case. We won't get into that. Don't ask me any questions about that. But here, these colors are really actually how they look. They're pretty spectacular. And so when you zoom down a very close to the surface, it's a little hard to see the telescope. You can't get that far down. I'm going to turn this right side up. But IRTF, the infrared telescope facility, is right here. This is the telescope I'm going to show a little bit about. I've been observing with that. I do observe from home now. It's not as nearly as good. The internet is pretty bad, but I have collaborators who help me out with this. And when we're all done with the pandemic, I'll be back observing. And the nice thing about observing here is you can observe actually at the telescope, which is not true for Keck, which I have observed here, but off the mountain. And the reason is that astronomers tend to fall over at 14,000 feet, not being acclimated. And I actually kind of like it. But I was going to pause for a little bit and just tell you a little bit about observing. And I keep in mind, these are the locations of the exoplanets. So what we're looking at is across the galaxy, these analogs to how our solar system and possibly these systems are formed, and really trying to understand exoplanetary systems and put our solar system in kind of a context that makes sense, and try to figure out, this is part of that big question: are we alone? How unique are we? And we're learning a lot about exoplanetary systems now that we weren't expecting. Like most planets form in binaries, and meaning a companion sun. But I'll just pause for a second. When you're on Mauna Kea, when you stay on Mauna Kea, you stay in a little lodge, and there's really beautiful scenery here. There's you can hike. There's not a lot of people here. My favorite plant is this plant here, which I'm going to show you plant photos. You probably weren't expecting those, but that's okay. You get to see them anyway. So this is the Mauna Kea silver sword, and it's highly endangered. It only exists on Mauna Kea. It was almost extinct due to ranching and cattle eating it several decades ago, and they're trying to bring it back. And one way to do that is to have this enclosure, and you can visit the enclosure. You wipe your feet off here, you go through here, and you walk around and see the silver swords. They're really spectacular. They live in this harsh environment. Now, this is not, when we think about, sometimes the comparison with Mars is, if you think about the best day on the top of Mount Everest, that's way better than, or the worst day, I should say, on the top of Mount Everest, that's still way better weather than you get on Mars on a good day. And so our Earth is really habitable. And so this is an extreme environment really for a plant, but when you think about life in space, Earth has still got the best environment for life. But nevertheless, this is extreme in the sense that it's high elevation. There's not a lot of precipitation. And so it really has to hold on to this moisture, and it gets very cold as well. The thing about the silver sword is it flowers once and then it dies, and they think it lives to be, it could be anywhere from a few decades to 50 or 60 years, maybe even longer. But you can see them in this flowering phase. So this is the end of this silver sword's life. And then we'll go up the mountain. And to remember, why do we observe it on Mauna Kea? Well, it's high and it's dry, and it's got the best number of weather nights, good weather for any location on Earth. And so being able to use a telescope on Mauna Kea is really great. This is called the marine layer, these clouds, and you want to be above them. That's the key. So you have to, you want to try to get as close to as dry as you can to get data from beyond our planet. So this is the NASA Infrared Telescope facility. It's a 3-meter telescope, so it's not the biggest telescope on the mountain, but it is an interesting telescope, and it has a really nice instrument that we can use for spectroscopy, for learning about the chemistry of these systems. One thing that's cool that I love about this telescope is it was built to support the Voyager mission. And that is a probe that's at the farthest reaches of our solar system now. In fact, it's beyond the farthest reaches of the sun, and it's headed towards what's called the Oort cloud, where our long period comets come from. So it's really it's the farthest we've ever sent any object. It goes 1 million miles a day. And one of the cool things from an astrobiology standpoint is it has these golden records. There's 2 probes. Each one has a golden record. This is the front side of the record and the back side of the record. And they're each equipped with one of these records. And this is code, essentially, for an alien civilization. If it ever got a chance to find this probe, which is really, really infinitesimally small chance that this will ever be found, that it would know kind of where we are. This is our location based on quasars, our location of quasars. This is to show we understand science. This is the hydrogen atom. And these apparently are directions that they can follow. Don't ask me what it means, but apparently if you're a smart alien, you can do it. And Carl Sagan was the one, sorry, that's an engine behind me. Carl Sagan was the one who convinced NASA to put this on. And that's, Carl Sagan really propelled, literally, the search for life and wanted a time capsule of Earth out there that would, if it's found, will probably be long gone. by that time. So this is this gets us to thinking about SETI and extraterrestrial intelligence and how do we communicate. And this is one way we can do that, is to send probes out that we may never know what happens to them, but yet it's important, he thought, to do that. So anyway, we can go to the summit and observe, and inside the dome, this is the big telescope, this is part of the telescope when you're inside. We observe right behind the wall in a room, and I'll show you that in a second, just for perspective. You always get to go in the dome.
Big telescope.
It's a big telescope. It's not even the biggest, but it's really cool, really, really cool. And it's like a spaceship on Earth. You're bringing light to yourself, and it's one of my favorite things to do as a scientist, honestly, is going to the telescope to observe. But when we observe, we're not looking through an eyepiece, we're actually looking at computers. And this is my collaborator who's in Oahu for this one, which is a different island. We look at these computer interfaces to operate the instrument. And right to the left of me is we have a support astronomer. It's a big operation to use these telescopes. You have a support astronomer who checks the weather, makes sure that the telescope is working appropriately. We have there's usually another person also who goes back and forth outside and checks the telescope. So it's a big operation, and that's why it's, it's a competitive to apply for time. And we've been very lucky with this project that we're working on to look at carbon and oxygen in these objects to get some time on this telescope. So what do the data look like? I'll just show you quickly. This is one star. This is if you see really closely, this is the black bar, which is the slit of the telescope. And these are winds coming off the star. We also have a binary. It's a little hard to see, but there are two objects here. So we can study these with this telescope. So this is a system with two stars, like two suns. And then the spectra, these long, nice long lines, this is carbon monoxide. And this is the data, what the data look like. And so the data, we can analyze these lines to try to understand carbon chemistry, essentially, and we get these spectra all across the galaxy. So we have energy and wavelength, and I'll say these lines are CO, carbon monoxide, which is really informative for early planetary chemistry. So we haven't been to the exoplanets, and we certainly would love to go, but we have artistic renderings. So I put this in here because people sometimes wonder what they look like, and sometimes you see these in the news. These are artistic renderings, so that means that an artist using real data was able to imagine what the surface of a planet could look like. And this is TRAPPIST-1, which is an exoplanet that was recently discovered among 6 other planets. So it's 7 planets, and 3 are in the habitable zone. And so that means there could be liquid water on the surface. And so this could be a planet we could go to one day, maybe, but I have to say it's probably unlikely.
This looks a little familiar.
Yeah, this is Luke Skywalker. The reason I put this on is that 2 suns were thought to be science fiction back when this movie was made, way back in the 70s and 1970s. And so this 2 suns was thought to be really exotic and unusual. But the truth is that these exoplanets here and beyond in our galaxy, most of them have more than 1 sun. And so what was science fiction way back when, now we have the data to understand that it's actually not, and that it's more reality. Oh, sorry, that was another slide. Okay, so we should probably move to Mars if that's okay.
I think so.
Yeah.
While we're heading out there, we had a couple questions pop up about spectroscopy.
Okay,
Can you explain the fundamental process and what kind of data gets taken away to make spectroscopy data useful?
Yeah, and I'll just say that question that always tells me I should have put in more spectra, but nobody ever wants them. So the question of how does it work, is that the main question?
Yeah, so you mentioned that there was carbon dioxide in those squiggly lines. Can you explain how the squiggly lines represent carbon dioxide?
How they represent that?
Yeah.
Okay, so it's actually carbon monoxide. So it's
carbon monoxide, pardon me.
And so essentially to make and I'm very pleased with this question, by the way. As a spectroscopist, I could talk the whole time to the dismay of the programmers that we're talking about spectroscopy. But I will just say this. So the reason we know these are CO, molecules rotate and vibrate and move around at different energies. That energy is translated to light and translated to wavelengths. There's a direct correspondence between energy and light. And so we know that these lines are certain transitions of CO because they've been studied in a lab. And so we know where they should be. And we can then observe them and say, okay, this is where CO should be at this wavelength here. do we see it? And we do in this case. And the reason we get these spectral lines is that the molecules are transitioning in energy in some way. In this case, with absorption, the absence of light, this is the star, this is the absence of light, so the lines go down, the molecules absorbing light at that wavelength. So you get this transition. These letters just mean a certain transition, R4, R3, R2, etc. So those molecules are there transitioning at those wavelengths. And you get transitions all over. And this is how we learn about the entire universe in terms of molecules and chemistry, which is really, really important for astronomy. And so we just know, we understand fundamentally what these molecules should be doing. We have tables of where they should be on a spectrum, and we can basically code in those tables with our codes and look for those lines. And we know that at 2 microns, we should see CO at these transitions. So that's basically what's happening. I hope that answers your question. Do you think that was that sufficient? You can let me know. Did you hang up?
As with careful analysis of the light, we can see the presence or absence of specific colors, and that indicates the presence or absence of specific
not colors so much. Yeah, not colors so much, but we look at sometimes with astronomy we see false color, and we see and so therefore with false color it's actually the chemistry. So it starts with understanding what molecules are there. And the reason we see them is we're able to analyze with a spectrometer what energies are, we say, okay, we set our spectrometer for 2 microns, like in the spectrum I showed you, we will be able to detect CO if it's there at those transitions, essentially. Because if CO is there, some number of molecules will be undergoing those transitions in energy.
Sounds great. We've got a glowing blue carbuncle on the surface of Mars, it looks like.
We're going to Olympus Mons. So as I'm talking, I'm also going to make it brighter. So I'm changing. You may see with OpenSpace, if it's dark, you can change it to light. You can make it day, essentially, which is really cool. And this is the largest volcano in the solar system. And we're going to zoom in. Go here. Oh, sorry, the largest planetary volcano in the solar system. There's an asteroid that has a bigger volcano. Vesta has a bigger volcano, but this is the largest volcano in the solar system. And again, it's a shield volcano. So this is our analog to Mauna Kea. And it is, if you were on Mars, it wouldn't really be like a looming mountain, even though it's about 2.5 times the elevation of Mount Everest, which is our largest mountain. So Olympus Mons, there it is. All right, so it's really spectacular. You can zoom down. And what you'll see here with OpenSpace too is sometimes you see these what look like rectangles. Those are just different data sets. We have an orbiter on Mars called the Mars Reconnaissance Orbiter that really supplies all of the data that we have for our solar system, more or less. But you can travel around Olympus Mons, and when you think about comparing our planet to others, Mars was habitable most likely in the past, and there was a volcano that likely erupted and was created just like we have on Earth, but then Mars lost its atmosphere and lost its oceans. Along that line, I think we're a little short on time, right, Josh? So
yes, indeed. We got about 10 minutes left.
10 minutes, all right. So I'm going to go to Jezero Crater, which is the landing site for Mars 2020. And remember Lake Salda, which we looked at
in Turkey.
In Turkey, exactly. So that was the analog to this lake, and I'm just going to make it day again. Come on. You can go faster than the speed of light with OpenSpace.
Always a handy superpower.
Which is a very handy superpower. Let me just make sure. I'll zoom down here. Let me go back to Jezero, and I'll make sure I get there, and then I'll turn off. I'll go back. There we go. All right, so now I'll go back to Mars. The reason I switch these is because it's easier you get a better driving experience. And I'll turn off my thing here. And so this ellipse here, this is the landing site for Mars 2020, roughly. They're going to land more or less around this area. And the reason it was chosen is because there's a water feature here. This is the region, this part, I'll just spin it a little bit. If you look here, moving my stuff. Oh, there we go. This river here, this is a river, this is an outflow channel. Mm-hmm. And so this outflow channel, and actually it would be nice if this was a little bit brighter.
I can see a nice little sinuous, windy pattern there.
That's it, right. So water absolutely, without pretty much, we know for sure, I would say, we know for sure water flowed on Mars, could even be flowing at times on Mars. And this is that channel that you see, and it's really amazing. And, it takes a little while sometimes for the data to load in with OpenSpace, but you do see it here, and you can follow this channel. You can fly down this channel, and you can go to the landing site of Mars 2020. There's a beach. You can see here, really amazing. These outflows, this delta here.
That's beautiful.
It is beautiful. It is. And then it's possible that we know from spectroscopy from the Mars Reconnaissance Orbiter that the mineralogy of this crater is very similar to what Lake Salda has, which is the result. Which is the result of microbes. Let me move that back so we don't go upside down. And you can explore that. You can go down pretty low. You can zoom in, and they're going to take samples around this beach area with a rover, which is really cool. It'll also have a drone of flying around, which is the first time that'll happen, and it's really pretty awesome. So if we think about microbes and we think about mats of microbes, building up. This is actually some of the first type of life that could have existed on Earth. And these are called stromatolites. These are microbial mats that could have existed on Mars when there was water on the surface. And so these mats are created by layers of microbial deposits. This is in Australia, in Shark Bay. And it's possible that there are fossilized versions of these on Mars when there was water on the surface. And we think, could water exist like this again on Mars? Could we terraform Mars and create another Earth with Mars? And we don't know the answer to that. It could be impossible with the technology we'll ever produce, or maybe it would take just a very long time. But eventually we may think of ourselves on Mars. And I really like this picture of maybe one day dropping the spacesuits and yay, we're in the beach. And so maybe one day we'll have this experience on Mars, but it could also be never. So you have to think of both scenarios.
Would have to be a very big change.
Yeah. And since we're a little short on time, I'm just going to zoom out, and I'm going to turn on, these are our exoplanets, and I'm going to, we'll fly to Europa, but I'm going to keep going, and I'm going to fly to Europa, and I'm also going to turn on, once we get there, I'm going to turn on the radiosphere, and we'll just end there, and I'll take more questions. What's happening here? Let me zoom out and go back to Europa. Let's zoom out a bit. Sometimes it's easier to get farther from your system.
So we had a quick question pop up. Is there a favorite spot for you for where humans should be looking for life in our solar system?
Yeah, in our solar system is a favorite spot. I mean, there's so many places to go and such limited resources. I think Europa is really exciting. I think I'm going to have to fly through this. I think I'm stuck. Hold on a sec. Sorry about that. Let me go back. I think Europa is really exciting. And I think that if we can get there and figure out a way to drill through the ice of Europa. Europa is a moon of Jupiter, and it has these really cool, here we are, we're here. It has these striations. There's likely a global ocean, which would be about 2.5 times more water than we have on Earth under the ice. These stripes are from salt coming up through the surface periodically. We know that water exists. We've seen evidence of water plumes. And I think if there's really any chance of life beyond our solar system, I think Europa is a great place to look. It's kept warm by the pull of Jupiter. And the question is, can we get there? There's already an orbiter going back, Europa Clipper, and we just have to figure out a way to drill through the ice and not contaminate it and figure out the technology, because we don't quite have that yet. So I'm a fan of Europa. I'm also a fan of Enceladus and Titan, which are moons of Saturn. But with limited resources, I think Europa is closer and is really, really exciting.
Mm-hmm.
So the last thing, while I'll take more questions, I'm going to turn on the radiosphere, and I'll leave it on. And that is, when we think about SETI again and the search for extraterrestrial intelligence, we think about, will we ever hear from aliens? Let me go back. Sorry, I have to go to my...
We actually had a really cool question pop up about that.
Okay.
Probability of life in other places greater than not having life. So the possibility, would you say, is leaning towards positive rather than negative because of the abundance of exoplanets?
That's a really good question. I think that the fact that we have exoplanets like Earth close to us and found so many of them, that the likelihood of aliens, intelligent life, communicating off those planets is very, very low near us, because we don't have any evidence for that communication near us. Because we have so many exoplanets, where are all the signals? It's like, where is everybody? That's the Fermi Paradox. Those big questions of, if there's so much potential for life out there, where is everybody? And we don't have an answer. But I will say, this is the farthest extent. These are some exoplanets right around us. This is local to us. This is like our next door neighbor. These are our neighbors. We can't get there easily. It's very expensive to create technology to even get to Mars safely. This is about 100 light years, roughly, from Earth. If Earth was in the middle, we've sent signals out from radio and television. I personally think that it's very likely there's life somewhere in our universe, if not our galaxy. But what resonates best with me, what resonates scientifically with me, is what Carl Sagan would say, and that is that space is, he said this great quote saying, space is vast and the stars are far apart, which basically we have to remember that most of space is space, and the distances are so enormous, and the time it takes to get anywhere from one place to another, beyond even our ability to do, is so enormous that there's certainly a possibility for life out there. I mean, he put the golden records on. He was a big proponent of astrobiology and SETI, but we probably won't ever know about it. And it's a very disappointing but sobering idea, is that we can't get very far. And we've developed a lot of technology. And so you ask, is what happens to intelligent civilizations? Well, maybe they destroy themselves because of the technology they develop that becomes very detrimental to their own survival, both from a planetary standpoint as well as from just developing like weapons, or destroying their own planet from an environmental standpoint. So I don't know. I mean, it would be great. I don't think they're near us, frankly. I think that it's very unlikely they're watching us and not showing themselves. It doesn't really make a lot of sense to me. But these are all conjectural, almost philosophical questions. But I think the possibilities, absolutely. I think it would be highly great. It doesn't make sense that we're alone, but whether we'll find out who else exists, that's a question that I'm not sure about. Yeah.
Agreed on all counts. So from out here, we can see a whole bunch of exoplanets, a pretty prodigious radiosphere. Are we expecting more exoplanets inside the radiosphere? Or is this probably all the ones there are?
A little bit of right. It's a little bit of, let's see, this is about 80 light years. 100 light years. So yeah, there will be some exoplanets in here. Our closest exoplanets are, the closest system is about 4 light years away. So that's Proxima Centauri. So there are some systems in there, but I'll just caution you that it's a little hard to tell with the visualization necessarily. You can see there's some exoplanets in here, but as it rotates, there's some behind it. So you might have a superposition illusion. I'm not exactly sure. I would have to look up exactly how many exoplanetary systems are within 100 light years, but it's, roughly, I don't know, maybe I want to get, I don't even want to guess. Someone will tell me I'm wrong, but it's.
We often tell folks about 100 or so.
Yeah, I was going to say a few hundred or 100 or something. Yeah. Yeah.
Well, very cool. Is there any last spot you'd like to visit, or should we head back home?
Yeah. I mean, the only other thing I was going to show, which I skipped, there was Europa. We can go to Titan, or we can go back to Mars. I actually like Titan, and the reason it's cool for astrobiology, and I'm going to turn off the radiosphere because but let me see. I'll just quickly, let me see. I'll do it from here. I like Titan I mentioned it briefly with in terms of astrobiology, for searching for, it's a really cool moon of Saturn, and it is interesting for two main reasons for astrobiology. The first reason, as we fly at the speed of light, we still have to wait. Micah, why do we have to wait? No, joking. Complaints. I'm kidding. That was a joke. OpenSpace humor. I'm guessing everyone's laughing. I can hear it.
Absolutely.
So with Titan, and let me get to Titan so I can turn off shading because it's such a little thing. Oh, come on. Sometimes their little menus are. Come on. There we go. I just wanted to turn it off since it's. There we go. Titan. Okay. So what you see on Titan is it has a really thick atmosphere. And this atmosphere is the dark regions could be actually what you're seeing here is without the atmosphere, unfortunately. And I didn't put a picture in of it, but basically it would look just like a solid ball. It wouldn't be very interesting. So we see here is without the atmosphere, and you see these dark regions are probably lakes, but not of water because it's very, very cold on Titan. So the lakes on Titan are probably hydrocarbons. So that means hydrogen and carbon, these carbon chains, these molecules. So methane, ethane, all these other more complex hydrocarbons, and we need carbon for life. And so there's some hypotheses that maybe there's life that could live in liquid hydrocarbons. So not liquid water, but liquid hydrocarbons and still be carbon based. And so that's a really interesting field of research. Some scientists at Cornell came up with a cell that they made. A cell in a lab that could survive the very extreme temperatures on Titan. And so there's theoretical life life that's been theorized that could maybe survive in the very negative 400 degrees or something on Titan. The other really cool part about Titan is that the thick atmosphere, it's the only moon with an atmosphere and like a substantial atmosphere and liquid water on the surface. Or liquid on the surface. Liquid, not liquid water. Liquid on the surface.
Liquid water.
Yeah, liquid on the surface and a substantial atmosphere that is like the primordial Earth. So by studying Titan, we can understand maybe more about our early Earth before life evolved. And so that is another exciting reason to go back to Titan. And we did land on Titan back in the 90s, I want to say.
Huygens?
The Huygens probe, part of Cassini. So I may have the dates, but yeah, we landed, and they hoped to land on a liquid part, but didn't. But still got really interesting data. We know that there's hydrocarbons, and to me, this is a really fascinating moon. I know we're going back with Dragonfly, which is a mission for the next few decades that's been planned. But that's really exciting. It's a small mission to go and fly around and get some more data for Titan. So this is a really cool moon to me from an astrobiology standpoint.
Agreed.
Yeah.
Well, thank you so much, Rachel. This has been
absolutely
super exciting to see the universe through someone else's perspective.
Yeah, this has been a lot of fun. I hope everyone, did I answer all? I hope there are no more questions. It's been a lot of fun to share with you guys. So thank you.
Absolutely. So thank you all for tuning in for our broadcast. If you want to find out more about we have amazing links you can check out. But if you're following up, there's one thing we would love for you to do. OpenSpace wants to hear your feedback on this program. So if you're able to, we just dropped a SurveyMonkey link right in there. You can go follow it, complete this brief survey, should just take a few minutes. And the first 30 people who respond get a super cool NASA meatball sticker mailed to them. So we really appreciate your feedback, number one. Number two, the stickers are really cool. And number three, again, thank you, Rachel, and thank you to everybody who tuned in today. Anything else you want to say?
No, just everyone be well and have a great weekend. And download OpenSpace and try it yourselves if you want. It's a lot of fun to play around.
If you're feeling stuck at home, there's nothing better than flying around the solar system or beyond to make yourself realize how big and awesome the universe is.
Yeah.
Well, thank you all again. Have a wonderful rest of your day, and we hope to see you again next Friday.